quite a bit of time on this section as well, and then that'll be our breaking point for our next test, which will probably be the last test before our final. We've been on this stuff for quite a while. It's probably roughly looking like December 3rd for our test. So we've had the week after Thanksgiving that we come back and work on all this, and then probably the following week we'll be ready for our test over everything. This will be one of the bigger tests that we've had. So, chain rule. Let's talk about this. When we have done things to the third power, like I made you guys do like a cosine to the third, and we had to write out all the derivatives, and you were kind of annoyed because it took a long time. And we basically just took the three things and we did one derivative at a time, and you guys kind of caught on to a pattern that you had three identical pieces there, and it simplified. That is actually kind of what motivates the chain rule. This is something that we can use when we have a function within a function. So things being composed. For instance, like if I had x plus 4 to the 5th power. You have an inside part, you have the x plus 4, and we have the outside part, we have the 5th power. Before now, the only way you could do this derivative would be to write this 5 times, multiply it all out, and do the derivative, or write it 5 times and do the product rule 5 different times and simplify. There is a shortcut called the chain rule. To do the derivative of that type of function, you do the derivative of the outside function, leaving the inside alone, times the derivative of the inside. So in this case, if this is my function, the derivative, you do the derivative of the outside part. So the outside part is my 5th power. So when you do something to the 5th, the 5 comes down and you subtract 1 from your power, right? So I'm going to have a 5, the inside stays the same, to the 4th power, times the derivative of the inside part. What's the derivative of x plus 4? 1 plus 0. 1. So this derivative is just 5 times x plus 4 to the 4th. Much shorter than writing it out 5 times and working from there.
Would we have to wait the epsilon history?
No. You can't just bring it in. You would have to write x plus 4 times and multiply it out, but no, we don't have to do that. Alright, so let's try another one. Let's find the derivative of y equals 3x squared plus 5 to the 17th power. Okay, I use, and I think I already put this on there, on your note slide. You might see like dy dx, and a lot of times when it talks about, if you look at the chain rule, it says you're doing dy dx, and that's dy du times du dx. It's really kind of a confusing notation. These are really whole expressions. It's not like you're just canceling those du's. It's just saying you're doing the derivative of the outside in terms of the middle. Then you're doing the derivative of the middle piece. So don't let that notation confuse you. Alright, so my derivative here, dy dx or y prime, derivative of the outside. So the outside part is that 17th power. So the 17th power is going to come down, inside stays the same. Subtract 1 from the power, so now it is 16 times, what's the derivative of the inside? 6x. We could simplify here. 17 times 6x. Times 3x squared plus 5. And that's our final answer.
You take the power of this one.
Okay.
3 times 2.
Questions right there. Certainly easier than writing it out 17 times and doing 17 derivatives there. Alright, let's just keep trying these. I need to rewrite this problem. Okay, so my derivative, what happens?
Bring the exponent out to the front.
Inside stays the same. Subtract 1 from the power times derivative of the inside. So simplify 1/2 times 2x would just be x times x squared plus 1 to the negative 1/2. Okay. Good. Example 3, I put 2 very similar problems here because I want to talk about the difference. How are those 2 pieces different? Tim?
Well, the first one you're taking the sine of x squared, and then the second one you're actually doing a sine of x times sine of x.
Right. On the first one, you're squaring the x itself. The second one, you're squaring the entire sine. So the difference here when you go to do your chain rule is the inside and the outside function. If I'm looking at this one, the first one, what's the outside function? That's your inside. Okay, when I talk about inside and outside, inside is the thing you do first. So if you're going to plug a pi in here, are you going to do sine of pi or are you going to square it first? On this one, you would square it first. So the squaring is your inside. So the sine is our outside. So chain rule says you do the derivative of the outside and the inside doesn't change. So the derivative of sine is cosine. And the inside doesn't change, times the derivative of the inside. So derivative of x squared. So we get 2x cosine x squared. On B, when it says sine squared, that means you're taking the sine of x and squaring it. So if you were going to plug a pi in first, would you square or do sine?
Sine.
You would do sine. So sine of x is the inside here. The square is the outside part. So chain rule says derivative of the outside. So the outside comes down. My 2 comes down. Inside stays the same. If I subtract 1 from my power, it's just to the first. Times, what's the derivative of the inside? Derivative of sine is cosine. So we just get 2 sine x cosine x. So that placement of the square changes the inside and outside function and gives us 2 very different derivatives there. Do you understand where you start on those? We really already said that. I'm going to skip that. I'm going to go to this. This is kind of leading us into a lot of what we're going to be doing in section 3.5. An oil refinery makes U liters of gasoline from X barrels of crude oil. Then they make Y grams of petrochemical from the U liters of gasoline. Identify the units of each of these things. So we'll talk a lot about different types of rates in here. And you'll find it's very, very important to be able to pick out the rates when you do these things. Remember, a derivative is really just a slope. You did slope back in Algebra 1, Algebra 2, college algebra. You know slope is a rate of change. So when you did those slopes, your units were something per something, right? Miles per hour, feet per minute, something like that. The y and the u, whatever your variables are, tell you which part to look at so you get your units. So when I'm looking at y, what are the units on y?
Grams.
So this is grams. divided by, so per, on this denominator I have U, and U is liters. So grams per liter. du dx, what would that be? Liters per barrel. Okay, what about dy dx? Okay, we're just going to keep practicing these. Why don't you guys try examples? Well, I'm going to give you a few minutes, see how many examples you can work through. I'll walk around and make sure you're on the right. So we have 100 x cubed minus 1 to the 99 times 3x squared. So you get 300x squared times x cubed minus 1 to the 99. Good. 6. So you bring down to -3. Inside stays the same. What's your new exponent? Good. Derivative of the inside? 10x minus 2. As far as simplifying from here, you could leave it like this. If you wanted, you could distribute the 3 through the second parenthesis and make it -30x plus 6. Certainly not necessary. So either of those versions of the answer would be okay. This one. So 2 minus 5x squared times 5. So you got -15 times 2 minus 5x squared. Okay, here I noticed you kind of slowed down a bit. We have a couple options. You could do the quotient rule with this.
Isn't it 0? Because if y is greater than 0, 1 is 0.
Well, you have to do low d high minus high d low for low squared. So the whole thing won't turn out to be 0, just the derivative of the top.
Let's do the -2.
It'd be much faster. So then we have -2 times 2x cubed minus x plus 7 to the -3 times derivative of the inside 6x squared minus 1. Again, if you wanted, you could run the negative through the -2 through that second parenthesis, but you don't have to. Alright, let's try 1 or 2 uglier ones and then we'll probably stop for the day. Okay. This one. So, outside is the 5th power, so 5, inside stays the same. Subtract 1 times, how am I going to do the derivative of the inside? Low d high minus high d low over low squared. Okay with that part. Let's clean this up. I am going to rewrite this as z minus 1 to the 4th power over z plus 1 to the 4th. This one, z plus 1 times 1 is just z plus 1. This would be z minus 1, but you have to distribute the negatives, so minus z plus 2 over the z plus 1 squared. Not 2. Sorry, I got a step back. No, I was thinking to the next step and I wrote wrong thing. Plus 1. What happens now? The z's cancel, and that's where the 2 comes in. 1 plus 1 is 2. Can we do anything else? Yeah. So we have z plus 1 to the 4th times z plus 1 to the 2nd, so that's z plus 1 to the 6th. On the top I'm going to multiply 2 times 5, and that gives me a 10. That was a little more involved. We had a couple different things going on in that problem. Questions there? Let's try one more. Have to do product rule. We have this thing times this thing. Okay. So product rule says you do one derivative at a time. So if I start with the yellow one, to do the derivative of that, what's going to happen? 5 inside stays the same. The 4th times, what's the derivative of the inside? Okay, all of this just represents the derivative of the yellow piece. So the product rule says it's the derivative of the first times the second one plus the first one times the derivative of the second one. So to do the derivative of this, the 2 is going to come down, inside stays the same. Subtract 1 from your power, so now it's to the first, times the derivative of the inside is the 3x squared. So all of this just represents the derivative of that second piece. You okay there? Clean up as much as you can. There's not a whole lot we could do. You know, the first one, if you wanted, you could distribute the 5 through the 1 plus 2x, because it doesn't have an exponent, but you don't have to do that. This one, at the very least, I would like for you to multiply the 2 and the 3x, and just go ahead and pull that 6x squared out in front. Now there are obviously other things. You could pull out greatest common factors and go from there, but you don't have to go that far. So you're welcome to. Sometimes we might have certain situations where we need to simplify a little more. but this would be an acceptable answer. So these derivatives are sometimes a little ugly at the end. Any questions on that? Should I do one more? Save it for Monday. Huh? Do it? Alright. Okay, let's look at this one. What are we gonna have to do here? Quotient rule. So, quotient rule is low, so the bottom. D high, derivative of the top. How are we gonna do the derivative of the top? Shame. So,
Oh my god.
so for the derivative of this, we have 3, 1 minus x squared, subtract 1 to the second, times derivative of the inside, negative 2x. There's low d high, minus high, so the top one, below, derivative of the bottom. So the 2 comes down, the inside stays the same, subtract 1 from the power, times, I'm going to now space derivative of the inside, 5 plus 12x. All over the bottom squared. If it was to the second power and I square it, it is now to the 4th.
Oh my goodness.
Alright, that is beautiful. What do you want to do?
Leave it like that?
We can do a couple things. Do you notice, is there anything that shows up everywhere?
That.
So we can cancel one of those out. I can drop this one of this, so it would take it down to 3 down there. Okay, I'm going to do my 3 times my negative 2x, so I get negative 6x times this